Today I'll be proving that in a vector space, if a linearly independent set of vectors has the same size as a basis for the vector space, then the linearly independent set is also a basis. Okay, so what I'll do is I'll let v1, v2 up to vm be a basis. So this is, the v's are going to be a basis, and I'll make the w's, w1, w2, and wm a linearly independent set within the vector space. Okay, so the v's are going to be linearly independent and spanning. So that's by definition of basis. So we need to also prove that the w's are a spanning set. That's our goal. Okay. So since the v's form a basis, we can write the w's as a linear combination of the v's. So each of the w's is a unique linear combination of the v's. So what we can do is write w1 as equal to, we can write it as a11 v1 plus a12, oh wait, I'll write it as a21 v2 plus plus am1 vm. w2 we can write as a12 v1 plus a22 v2 plus am2 vm, and go up to wm equals a1m v1 plus a2m v2 plus up to amm vm. So all the a's are the coefficients that form the linear combinations. Now we can represent this in matrix form. So we can write a row of all the vectors w, and this will equal, we write a row of all the v's, and here we'll make a matrix A. This will be matrix W, this will be matrix V, and matrix A will look like this. That will be A21 up to AM1. This goes across to A1M and down to AMM. This is A. Okay. I've got an M times M matrix A, and just to confirm, so these linear combinations can be expressed using this matrix equality because, for example, the first equation is represented by the W1 corresponding to the A11 V1 and A21 V2 up to AM1 VM. Okay, so what I'll now prove is that matrix A is invertible. So it's M times M, so I'll prove matrix A is invertible. Okay, so what I'll do is assume, so I'll prove by contradiction, assume A is not invertible. If A is not invertible, it means when A is row reduced, so converted into row echelon form. So when A is row reduced, you're going to have at most m minus 1 pivots / leading columns, which means when you solve the homogeneous equation AX equals 0, you're going to have at least one free variable, and this means there is a non-zero solution. So a non-zero solution to AX equals 0 exists. So a non-trivial solution. Okay, so this means let's make C equals C1, C2 up to Cm be the non-trivial solution. So the C's are not equal to the 0 vector, and let this be the non-trivial solution. So now we have W equals VA, and so we have AC equals 0 also. Now what happens if I multiply C on both sides like this? So using associativity of matrix multiplication, I have V times AC. This is V times 0, and this is equal to 0. That means WC is equal to 0. But WC is, so that's W1, W2 up to Wm, and C1, C2 up to Cm. This is equal to C1, W1 plus C2, W2 plus. Okay, so this is a linear combination of the W's that give you 0. However, since from earlier we know that the W's are a linearly independent set, it means all the C's must be 0, which means C must equal 0. But this is a contradiction, because we assumed C was not equal to 0 at the start, so this is a contradiction. And this means, since we assumed at the beginning A is not invertible, it means this assumption was wrong. So in fact, A is invertible. So this is false, so A is invertible. Okay, so okay, so now since W is equal to VA and since A is invertible, we can multiply by the inverse on both sides, and using associativity again, we get V times the identity matrix, which is V. So W times the inverse of A is equal to V. And let's say let B equal to the inverse of A, and this means W times B is equal to V. Okay, so W times B equals V, and we can write B as an M times M matrix, such as this one. So we have an M times M matrix like this one. So now what we can do is, this is enough to prove that W is a spanning set. This is because, let's take an arbitrary vector x. So let's take an arbitrary vector x, and we can write this as a linear combination of the v's. Let's say we have lambda 1 v1 plus lambda 2 v2 plus dot 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 plus lambda m vm. This can be rewritten as using a row vector and column vector. So we have, write it as the v's in a row times the lambdas in a column. Okay, now let's say the lambda vector, let's say the lambdas, so let's say this matrix is equal to G. Okay, this means if you write WB equals V, and now multiply both sides by G, we have WBG equals VG, and VG is equal to X. And using associativity, we have W times BG is X. And so B is an M times M matrix, and G is M times 1, which means if we let H equal to BG, this is going to be an M times 1 matrix as well. So we can write W, so we can write the W matrix is W1, W2 up to Wm. The H matrix we could write as H1, H2 up to Hm. This is equal to, we have coefficients in front of the W's. So we have a linear combination of W's giving us our vector x. This shows no matter what x is, we can use the linear combination. We first use the linear combination of v's to get x, and this can be converted by multiplying matrices b and g. We can convert it into a linear combination of the w's that give x. So this is sufficient to prove that W is a spanning set. So W is also spanning, and this proves that the W's form a basis. Okay, so this concludes the proof that if you have a linearly independent set of vectors with the same size as a basis, then that linearly independent set is also a basis. Okay, so that concludes the proof. Hope you enjoyed this video. Thanks for watching, and I'll see you next time.